What you're listening to right now is interstellar space. What you're hearing are waves of plasma recorded 11 billion miles from Earth by the first human object to ever reach interstellar space. This is the space beyond which the stream of our sun's solar wind, traveling outward at almost 900,000 miles per hour, stops completely as it runs into the wider galactic current, the interstellar medium. This is the space between the stars, and these are the sounds recorded by the Voyager 1 spacecraft, the first ever human-made object to pierce through the outer walls of the sun's heliosphere. These sounds represent humanity's first steps into the interstellar current in which we drift around the Milky Way in a 250 million year orbit. The edge where our star's solar outflow meets the collective currents of the interstellar medium are analogous to how the pressurized water flowing out of your kitchen sink faucet strikes the flat, upwardly inclining bowl below. It radiates rapidly out from the point of impact until it's eventually checked by the calmer surrounding water, forming a turbulent hydraulic bore. This sudden decrease in the outward flow is similar to the chaotic mixture of electromagnetic forces and particles that happens at the termination shock, where the solar winds experience an abrupt deceleration as they reach the wall of pressure building up on the other side of a narrow band called the heliosheath. As the two galactic currents balance, this causes compression in a distinct change in the outwardly oscillating solar magnetic field. The heliosheath is the relatively narrow band of the heliosphere beyond the termination shock, and ending where the solar winds ultimately stop, the heliopause. The heliosheath's inner edge lies approximately 90 astronomical units, or Earth-Sun distances about 90 million miles, or about 3 times beyond the orbit of Neptune from the Sun. Here, the solar wind is slowed, compressed, and made turbulent in a foamy zone filled with magnetic bubbles 100 million miles wide. These magnetic bubbles are created by the violent impact of the solar wind in the interstellar medium, with some likely being the detached magnetic field bubbles that have broken off from the planets themselves and stream outward with the solar wind. At the final boundary of the turbulent heliosheath, the solar winds stop and completely give way to the galactic flow of the interstellar winds created by the billions of stars in our galaxy. At the heliopause, 35 years into its journey toward the boundary of our solar system, the plasma wave detector on the Voyager 1 captured these sounds of dense plasma ionized gas washing over it as it traveled through the heliosheath and emerged out on the other side of the heliopause, out into the vibrating medium immediately beyond our sun's total influence. In early 2012, Voyager 1, having already punched through the termination shock and having been traveling in the turbulence of the heliosheath's magnetic bubbles for years, suddenly detected the expected 80-fold increase in galactic cosmic rays from the interstellar medium. This was joined by an equally sharp drop in protons from the solar wind. These concurrent events were telltale signs of Voyager 1's imminent arrival at the heliopause, and were just the data astronomers had expected. Later that year, in November of 2012, Voyager 1 was hearing interstellar sounds for the first time, as it became the first artificial object to come in direct contact with the exotic galactic phenomena outside our protective solar cocoon. However, 6 months later, another wave of plasma appeared, this time louder and even higher pitched at a higher frequency. The interstellar medium appeared to be getting thicker, and quickly. This was something scientists hadn't expected. Space is generally thought of as a vacuum, but it isn't completely. The density of matter is extremely low, but it still exists. In the solar system, the solar wind has an average proton and electron density of 3 to 10 particles per cubic centimeter, while the mean electron density of the interstellar medium in the Milky Way, out among and between the stars, has been calculated to be around 0.037 particles per cubic centimeter. This is 100 times less dense than inside our solar system. As the Voyager probes first crossed beyond the heliopause, their plasma wave science instruments detected the electron density at 0.055 electrons per cubic centimeter, not too far from expected measurements. Voyager 2, which took the long way around, flying by Jupiter, Saturn, Uranus, and Neptune, and crossing the heliopause 6 years after Voyager 1, in November 2018, found a similar plasma density of 0.039, very close but slightly less than Voyager 1's measurement. However, after traveling another 20 astronomical units, AU, or nearly 2 billion miles beyond the heliopause, Voyager 1 reported an increase from 0.055 to 0.13 electrons per cubic centimeter. And detections made by Voyager 2 in 2019 showed an even sharper increase, from its lower 0.039 all the way up to 0.12. These represented about a 3-fold increase in plasma density in the immediate local interstellar medium right outside the heliosphere. Given that plasma at Earth's atmospheric pressure has an electron density of 10 to the power of 13 particles per cubic centimeter, that's 10 with 12 zeros after it. These amounts measured by Voyagers 1 and 2 outside the heliosphere may seem tiny, but they're significant enough to warrant our interest, especially since it's not clear what causes them. One theory is that the interstellar magnetic field lines become stronger as they drape over the heliopause from their source 10 billion miles away. This could generate an electromagnetic instability that depletes the plasma from the draping region, which would make sense as Voyager 2 did detect a stronger magnetic field than expected when it crossed the heliopause in 2018. Another theory is that the material blown by the interstellar wind should slow down and back up into a thicker, denser sheet of plasma as it reaches this outer boundary where the pressures between the interstellar medium and the solar winds flowing outward at such a high velocity mix turbulently and then eventually balance each other out. And these sheets, or these dense walls, have possibly been detected by the probe New Horizons, which in 2018 picked up the faint ultraviolet glow that indicated a buildup of neutral hydrogen at the heliopause, creating what's been called a hydrogen wall. Astronomers think it's possible that both explanations play a role. Future measurements taken by both Voyager probes as they continue their journey out into interstellar space could help figure it out. Like the ocean, the interstellar medium is full of turbulent, superimposed waves, sometimes interfering in constructive or destructive ways with each other. If our heliosphere is a ship sailing interstellar waters, then Voyager 1 is a life raft just dropped from the deck, determined to survey the currents. For now, any rough waters it feels are mostly from our heliosphere's wake, but farther out, it will begin to sense the stirrings from sources deeper in the cosmos, and eventually, our heliosphere's presence will fade from its measurements completely. The largest of these extra solar winds come from our galaxy's rotation as space smears against itself, setting forth undulations tens of light years across. Smaller but still gigantic waves rush from supernova blasts, stretching billions of miles from crest to crest. The smallest ripples are usually from our own sun, as solar eruptions send shockwaves through space that permeate our heliosphere's lining. And as these waves reverberate through space, they vibrate electrons around them, which ring out at characteristic frequencies depending on how crammed together they are. The higher pitch of that ringing, the higher the electron density will be. These various density measurements of the interstellar medium, they affect our understanding of the shape of the heliosphere, and beyond that, how stars form generally. And they even help us understand our own location in the Milky Way Galaxy itself, giving us a deeper insight into our place in the universe. Over 70 years before Voyager 1 would pierce through the heliopause, representing humanity's first emergence into the wider interstellar medium, a young boy at just 5 years old would walk independently to his local library, where one day he went to a librarian and asked for a book about stars. And the answer, he said, was stunning to him, that the sun was a star, but really close, and the stars were suns, but so far away that they were just little points of light. It was then that the scale of the universe suddenly opened up to him. He described it as a kind of religious experience. There was a magnificence to it, he says, a grandeur, a scale which has never left me, never ever left me. That young boy was Carl Sagan, and would grow up to be one of the chief scientific advisors to NASA for the Voyager missions, among many others. 20 years before Voyager 1 made it all the way out to the edge of the heliosphere, on February 14th, Valentine's Day of 1990, Carl Sagan and others advocated that they write a computer program to be sent out to Voyager 1, telling its thrusters to turn it around and look back towards its origins. That day, at an unprecedented distance of approximately 6 billion kilometers, 3.7 billion miles, or 40 Earth distances from the Sun, as part of a family portrait series, Voyager would take photos from its vantage point of all the planets, but the picture caught of Earth would be by far the most profound. In the picture, out of the 640,000 pixels that make up each frame, Earth's apparent size was less than 1/8 of a pixel. The planet appeared as a tiny, pale blue dot against the vastness of space. And coincidentally, given that the camera was aimed in close proximity to the Sun, our little pale blue dot appeared suspended in a ray of light, as if to highlight the preciousness of this one hospitable, Edenic orb drifting in the harsh, cold expanse of the universe. Carl Sagan, in his 1994 book, Pale Blue Dot, famously comments on what he sees as the greater significance of the photograph. In a condensed version, he points to the photograph and tells us to consider it again, to consider that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know,
everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Sagan was known to write beautifully and elicit the almost spiritual reverence one feels when studying the cosmos. In fact, he wrote frequently about religion and the relationship between religion and science, expressing his skepticism about the conventional conceptualization of God as a sapient being. For example, he says, some people think of God as an outsized, light-skinned male with a long beard, sitting on a throne somewhere up in the sky, busily tallying the fall of every sparrow. Others, for example, Baruch Spinoza and Albert Einstein, considered God to be essentially the sum total of the physical laws which describe the universe. But Sagan says, I don't know of any compelling evidence for anthropomorphic patriarchs controlling human destiny from some hidden celestial vantage point. But on the other hand, a God worshipping the existence of physical laws is emotionally unsatisfying. It just doesn't make much sense to pray to the law of gravity. Shortly before his death from cancer in 1997, Sagan actually replied to a question about his religious beliefs, answering that he was agnostic. And although Sagan thought that spirituality should be scientifically informed, and that traditional religion should even be abandoned and replaced with belief systems that revolved around the scientific method, he also emphasized the mystery and incompleteness of the scientific field. Regarding spirituality and its relationship with science, Sagan stated that spirit comes from the Latin word to breathe. He said, what we breathe is air, which is certainly matter, however thin. Despite usage to the contrary, though, there is no necessary implication in the word spiritual that we are talking of anything other than matter, or anything outside the realm of science, including the matter of which the brain is made. But he admits on occasion he feels free to use the word spiritual. And he goes on to say science is not only compatible with spirituality, it's a profound source of spirituality. When we recognize our place in an immensity of light years and in the passage of ages, when we grasp the intricacy, the beauty, the subtlety of life, then that soaring feeling, that sense of elation and humility combined, is surely spiritual. Like Christopher Hitchens or Sam Harris or Richard Dawkins, Carl Sagan's views might be characterized as scientifically materialist, trying to reduce all of human complexity and neuroscience, neurocognitive abilities into simply particles and electrical signals exchanged between them. However, I don't think it's appropriate to characterize Sagan's view of the universe and our experience within it as simply one of cold matter interacting on some trivial corner in a meaningless universe. I think his impulse to even mention feelings of awe and reverence and joy and humility from the interactions and the exposure to the deep levels of the universe that science allows for is an indication of his agnosticism in the face of the ultimate questions about the universe, its origins, and maybe even its purpose. And I think he was aware, as hyper-intelligent as he was, of the risks of nihilism, of adopting a position of meaninglessness and reducing the human experience, all the emotions of love, anger, hatred, joy, pleasure, curiosity, interest, our very consciousness, to reduce that to mere biochemical processes, scientific materialism can strip away any perceived depth and significance a personal and shared experience might evoke. And it's dangerous to adopt this immediately and haphazardly without having critically thought it through and, as Sagan emphasizes, maintaining a stance of humble agnosticism before allying yourself with one side or the other of the age-old religious debate. I'm editing and I just realized I forgot to mention a quote that I thought was especially relevant to what we're talking about right here. It's from his novel, Contact, which is the only work of fiction he ever, at least publicly, published. And interestingly, the quote originates with his wife, Andrian, who was co-author of many works with him later on in life. So she was a collaborator of his and his wife, and also most famously helped co-write the book in the TV series Cosmos. And the quote is, "She had studied the universe all her life." This is talking about the main protagonist, or the protagonist who is an astronomer who discovers an alien message embedded in a signal transmitted to Earth, received from a telescope facility she was working at. And she had studied the universe all her life, but had overlooked its clearest message. For small creatures such as we, the vastness is bearable only through love. And just recently, Carl Sagan and Andrian's daughter, Sasha Sagan, wrote a book about meaning in our age of nearly predominantly secularism, at least in the West. And she used for the title of that book part of this quote, "For small creatures such as we." And I'm about to play a clip and I'm going to let her explain how she perceives, why she wrote the book, how she perceives the universe, given that her dad was a famous scientist and agnostic and very much elevated the status of science, or prioritized it over religion. And I don't want to be accused here of smuggling in Jesus, as Sam Harris says. So I just want to be upfront that although I grew up in a Christian household, and I'm probably of a temperament that I'm inclined to want to look for deeper meanings in life than just a cold, dead scientific materialism, I don't readily subscribe to any particular variety of Christianity. And I am very agnostic as well. I'm looking to be as rational and as I'm looking to avoid having to use faith and having faith wherever I can. So I don't want you to think I just blindly elevate religion over science, where science has obviously found answers. But I also don't want to discount the value and the value in the origin, the deep origin of so many of humanities, not just the West and Christianity and that tradition, but the morality that has arisen over thousands and perhaps tens of thousands of years in cultures all around the world, given that we are apes that have elevated our intellectual abilities over thousands, tens of thousands of generations, surviving in the elements and expanding across the globe over hundreds of thousands of years. It's an ethic, the idea that an ethic emerged over enough generations, over enough interactions and, births and deaths and individual consciousnesses. You think about how many geniuses must have existed in the last 100,000 years, given that humanity is at least 200, if not 300,000 years old as a species. The shamans and the leaders and the individuals, the inventors in the pre-scientific, prehistoric era that contributed to the sum total of the knowledge that has been telescopically compressed into these very concise creation myths and the oldest parts of our religious texts and traditions, I don't think can be discounted. And I don't think it's wise to just throw them out without trying to glean some of the most valuable nuggets of wisdom that has been hard-earned from the blood and tooth, nature red and tooth and claw character and environment out of which we rose. So I just wanted to put that disclaimer before any of you guys think, I'm trying to smuggle in Jesus or a religious point of view, an overly unnecessary religious point of view. I am open to it, and I am interested in it, but I am not overtly Christian or religious in any traditional sense, at least. Because I always hate when people bait and switch, they're not upfront about their beliefs and their faith or lack of it. But to bring it back to Carl Sagan and his daughter Sasha Sagan, I think it's very interesting that she decided to write a book about meaning in a secular age. So here I'm going to let Sasha Sagan explain in her own words what that quote means, why she chose it, what it added to her view of the world, and what, maybe it can give us some insight into Carl and Andrewian's beliefs and morality, I guess. There's an interesting little segment at the end that I'm going to include. She, in the Q&A portion, is asked by a guy who references the only work of fiction her father and Andrewian, I guess, ever wrote, and that without giving too much away, one of the core plot elements of the book is that the nature of the universe is one that has been designed and created. He asks a very interesting question regarding Carl Sagan's belief and why he would choose to have in his novel a creator of the universe. And I think this feature of the novel, of the universe he created in the novel, so to speak, really speaks a lot about Carl's belief that he, to me, I interpret it as he yearns to have a creator, but he yearns to have it be situated behind not just the morality, but the science and the beautiful mathematics that we have so far uncovered that underlie the laws of physics. So not only are there potentially laws of morality that are, transcend the here and now and truly are applicable and unchanging ways to orient yourself in the world, morally, behaviorally. He leaves room for that. But in his novel, he is, by having an intelligent creator, again, I don't want to give too much away, but he sent this, what's the word? He integrates science and mathematics into the character, the revelation at the end of the story, I guess. He integrates it, and in my mind, that is emblematic of Carl's belief, is that there is a science and a religion, and the two don't have to be antagonistic. And the questioner asks Sasha about this, and, well, I'll let you see her answer.
I'm so happy to be here. The title of my book is For Small Creatures Such as We, Rituals for Finding Meaning in Our Unlikely World. And the first part of the title comes from a line in the novel Contact, which is the only work of fiction that my dad ever published. My dad was the astronomer and educator Carl Sagan, and he and my mom, Andrienne, who's a writer and producer and science communicator, collaborated on many books of nonfiction, essays, the television series Cosmos, but Contact was the only sci-fi, the only fiction that they wrote together. And it was actually my mom who wrote the line that the title of my book comes from, which is, "For small creatures such as we, the vastness is bearable only through love." And that became kind of a family mantra for a philosophy that my parents communicated to me and to millions of other people. This idea that the more information we have, the smaller we are in the grand scheme of things. Well, then, what do we have? What can keep us from falling down the existential crisis of that sense of panic that we can all feel when it's like, the universe goes on in all directions. We're in this tiny, out-of-the-way planet. Well, what do we have? And the answer that they gave me was, we have one another, and we're together at this moment. And that filled me with a sense of real emotional fulfillment. The word spiritual has this sort of religious connotation, and I grew up in a very secular household where science was the pathway to understanding, and not just to, facts get kind of like maligned as like cold and hard. But my parents raised me with this idea that the real provable elements of life were beautiful and stirring and could give us that sense of connection with one another, with our place in the grandeur. An example I often think of is like this idea of like, if you were to tell a small child, there is a secret code in your blood that connects you to your ancestors, to everyone who ever lived, to the earliest humans, to the first life on Earth, and whether you believe in it or not, it's there, and it can tell you who you're related to and how closely. If you have a couple great science teachers in school, you might get that sort of beautiful thrill of those moments. But so often the things that are, like DNA, so often the things that we learn at a young age are presented in this way where the wonder and awe gets taken away from it. And, the word spirituality has this religious connotation, but I think it also can describe that feeling that wells up in your chest when you have a deep understanding of our place in the universe or how we're connected. And I think that every family is doing that on some level, whether you're explicitly talking about it or not. One day I went to my parents and I was like, Maruja says that when you die, you're in God with heaven, and you guys say that it's like you're asleep forever without dreaming. And my parents, in unison, like joyfully said, nobody knows. And that was like so revelatory for me, because it was like, if we don't have an answer to this question, we're not going to just put something there, because it's so painful sometimes to just have this open space. And I think that's something that really stayed with me and was so valuable, and something that I still think about all the time.
So it is kind of a vague, open-ended question. So first of all, it's really interesting that you said that Contact was originally supposed to be a movie before it was a book.
Yeah.
As is so often the case. I mean, I love the movie. I think the book was better. What really got me about the book was that it seemed like the most intelligent discussion I've read of science and religion. I thought it was really cool. But then, at the end of the book, right, in the epilogue, right, the computer, the Argus computer, discovers that the conclusion is that they basically prove that the universe was created on purpose, which I just thought was a really interesting way for a scientist like Carl Sagan to end that book. And I just wonder what you can say.
I think I have to just, I think that is a question for my mom, who would be able to answer that much more deeply, and was much more, I mean, she was like very deeply involved in every step of that, and she could give you a much more, I'm going to ask her. I can't wait to find out. I'll find a way to get you that answer. That's a great question.
So while I give Sasha credit for deferring and not presuming to have the answer, I just think, given the context of the fact that she chose specifically to write a book about meaning, and she chose to title the book from a quote out of her father and mother's only work of published fiction, in which the importance of love and potentially transcendent meaning across the cosmos is such a prevalent part, I think that's an oversight on her part. But I did think it was an interesting insight into Carl Sagan's mind, that for how intelligent as he was and how much he knew about the universe, he still very humbly left room for the unknown. And I hope to emulate him on this channel, doing just that, not promoting things that are, stretch the imagination too much and are too unreasonable to promote. Just simply learning what I can and trying to maintain a stance of humility and open-mindedness, while also looking for things that can anchor us and ground us in reality. The reality of material, the reality of the energy and dynamics, relations between not only material objects, although the deeper down you go, the word material becomes more hazy. But the relationship of objects that have evolved over billions of years to become self-aware and to become conscious. In the relationship of those conscious objects between each other and between generations. I think he was well aware that if we neglect the existential question, the spiritual question of our existence and any sort of meaning that might lie under, within, and throughout our experience, but not just ours, our experience with others, and our experience in the context of us as beings in a universe whose true nature we don't yet really understand. Neglecting these questions can leave us without a framework for understanding life's purpose and our place in the universe. It can lead to a moral relativism, a potential moral disorientation, an alienation and isolation that leaves us without anything anchoring us to reality. And I think it's important, and I think Carl Sagan knew it was important, to anchor our sense of self, our community, in our adventure, our behavior, and what we think we're doing in the universe, in the reality given to us by science, but in a importantly agnostic and humble manner that leaves open all of the territory as yet unexplored by the powerful discipline, including the territory of the mind. Over 300 years before Carl Sagan would echo him, referring to the Earth as a pale blue dot upon which all human activity, all our trials and tribulations, all our love and our loss occurs. One of the leaders of the scientific revolution, the Dutch mathematician and astronomer Christian Huygens, referring to the stars, said how vast those orbs must be, and how inconsiderable this earth, the theater upon which all our mighty designs and navigations and all our wars are transacted, is when compared to them. But in his book Cosmos, Carl Sagan emphasizes that the cosmos, being all that is, or ever was, or ever will be, they stir us. There's a tingling of the spine, a catch of the voice, a faint sensation, as if a distant memory of falling from a height. We know, when studying and learning about the cosmos, that we are approaching the greatest of mysteries. The size and age of the cosmos are beyond ordinary human understanding. Lost somewhere between immensity and eternity is our tiny planetary home. And yet our species is young and curious and brave and shows so much promise. Instead of belittling our existence, next to the magnitude of the cosmos, Carl Sagan he invites us to experience the exhilaration, the awe in learning about the cosmos and our place within it. He says our discoveries of the last few millennia remind us that humans have evolved to wonder, that understanding is a joy, that knowledge is a prerequisite to survival. He says, I believe our future depends on how well we know this cosmos in which we float like a mote of dust in the morning sky. And the surface of the earth is the shore of the cosmic ocean. And when studying the cosmos, confronted with the magnitude of both distance and the enormity of time involved, it puts you in a place to consider the enormity of time that humans have been evolving on the earth. And I want us to take a moment to think about our evolutionary trajectory and just how recent everything that we know, everything that we consider a part of human culture and activity really is. Humanity emerged evolutionarily 300,000 years ago. But far before them, 3 million years ago, our pre-human ancestors, a species called Homo erectus, had already been chipping stone tools, creating blades of stone with sharp edges to help them hunt and butcher their killings and probably engage in warfare. And for a couple million years after that, nothing really changed. Then about 1 million years ago, Homo erectus and other diverging species coming out of them or parallel to them evolutionarily, such as Homo heidelbergensis, they began spreading across Eurasia, out of Africa, far into France and Indonesia, and they began mastering fire. Until by 800,000 years ago, still hundreds of thousands of years before our modern ancestors first ever emerged, they were mastering fire and regularly cooking their meat. Now by 300,000 years ago, humanity, modern Homo sapiens, the ancestors of you and I, had emerged. And by 100,000 years ago, we were already cooking meat, using jewelry, fishing with hooks. Sometime over the next 50,000 years, we began using bows and arrows, burying our dead, even engaging in seafaring. It's thought around this time that we developed language. Perhaps it took tens of thousands of years. Maybe it was 100,000 years. But it was the most important change that took place to change how we interact with one another and even how we interact with ourselves, advancing the ability to think. Cave art, dating back almost to 100,000 years ago, shows that we had already begun to make depictions and then more abstractly manipulate symbols. And by 50,000 years ago, that's 45,000 years before the first ever writing, archaeologists have already found evidence that sculptures alongside the cave painting existed. Sculptures of ivory, stone, bone. And these implied a form of spirituality, generally interpreted as either animism or even early shamanism. These Paleolithic humans, living as hunter-gatherers, were gathering around a campfire in a cave, telling stories with language, depicting narratives of their ancestors from who knows how many tens of millennia into their past, on the walls of the cave with their cave art, lit in the ambience of only a flame, made with minerals, blood, other ornamentations. Who knows what music they may have added in addition to this? Who knows what rituals they might have had? Who knows what spiritual beliefs, being so intimately connected with the earth, these people from 50,000 years ago might have held? And who knows how crucial the information encoded in these rituals and these spiritual beliefs might have been for the long-term, multi-generational survival of these early ancestors. Who knows how important it was for this information to be transferred across tens, hundreds, maybe even thousands of generations of shamans and the tribes that they were responsible for guiding in a wise and fruitful manner. just as it was existentially crucial for each generation to pass down knowledge of the external environment, the practical, physical wisdom of living off the land, tool making, fire building, finding watering holes and times and seasons and eras of drought, recognizing and remembering animal migration patterns to follow and procure resources out of. There must have been behavioral knowledge, whether it's interpersonal, intertribal, or intergenerational behaviors that would have been crucially selected for, again across tens of thousands of years, in this prehistoric, very much pre-scientific time, when those that were uncooperative, those that were overly warlike, those that were prone to radical individualism within their group wouldn't have survived the most dire situations and the most desperate natural disasters, disease, external predation, whether it's by other groups or actual large megafauna predators. Who knows how important a sense of unified meaning and purpose was for the cohesion of not only the group, but of the individual minds that made up the group, the robustness, the resolute assuredness of belonging and affinity and familial connection to your group and its beliefs, and at the most profound level, the universe and the cosmos as a whole. It's interesting how many religions across the world invoke the concept of the emergence of reality out of a dark, primordial, chaotic abyss, with light and typically water springing forth through the divine act of creation or inspiration, injected into this amorphous, nebulous, timeless void. And this includes, importantly for Western civilization, the book of Genesis, being the opening book to the foundational document upon which all morality and ethics in the West is historically based. And it's thought that the beginning of the book of Genesis, one of the oldest extant religious texts that we have, although only first written down 2,500 years ago, probably emerged orally far earlier than that. Maybe 15, maybe 20, maybe 40,000 years ago. And what's interesting, despite your aversion or affinity for or to religious texts and beliefs, and despite the futility of a strictly literal interpretation of any religious text, you must understand that the pre-scientific mind and the geniuses who would otherwise nowadays, although possibly having religious tendencies, would also have tendency to be the scientific geniuses and minds of our present age. And they were compelled just as much to explain the world, the external phenomena of the world, as they were to explain the internal, moral, ethical phenomena, guiding their behaviors and actions and those of their tribal members around them. In Genesis 1, the first sentence remarkably overlaps with both the beginning of the universe, as we understand it cosmologically, and the beginning of our solar system. Our book here says the solar system is the region of space that falls within the gravitational influence of the sun, an ordinary yellow star that has shone steadily for almost 5 billion years. No one knows for certain what caused the initiation of the collapse that began what was to become the solar system. Happened 4.6 billion years ago from a gigantic cloud of gas and dust, the solar nebula. In the beginning, when God created the heavens and the earth was a formless void, and darkness covered the face of the deep. Now, a nebula the size that it would take to become what our solar system, or any solar system for that matter, became, would have stretched over light years. The distances between stars in our area of the galaxy are typically on the order of a couple light years apart. Now here we can see, between the stars, contrary to popular belief, the interstellar space, isn't empty. The ISM, the interstellar medium, is fundamental in the process of star formation and galaxy evolution. Temperature defines the material's appearance and the processes occurring within and around it. You can have dust clouds of denser, larger particles. You can have reflection nebulae. The density of the dust here is sufficient to produce a noticeable optical effect. The nebulae appear bluer because the shorter wavelength bluer light, just like in our sky and our atmosphere, is scattered more efficiently. Red scattering is more minimal, and the blue is more visible, less quickly absorbed. You can have dark nebulae, cool clouds composed of dust and the molecular form of hydrogen. They're only observed optically, like the Horsehead Nebula, against a brighter background. They absorb light and re-radiate the energy in infrared wavelengths. Stars are formed when dark nebulae collapse. We can have emission nebulae. The interstellar medium is heated by stars. The hydrogen is then ionized, producing the so-called H2 region, where the electrons freed by the ionization process, getting hit by the ionized radiation of ultraviolet and beyond, that knocks the electrons out of their orbit, and the continual emission and reabsorption emits a constant stream of red light. Now it's thought that our solar system started as a huge cloud of dust and gas, many times larger than our present system. This loose cloud would have probably made multiple stars that would have traveled along with our solar system, and perhaps Alpha Centauri and other nearby stars within a few tens of light years even of us would have been part of that cluster. It would have been unimaginably large. It would have been dark, would have been cold, negative 382 degrees, and it would have been spinning very, very slowly. Next, under the influence of gravity, the solar nebula condensed into a dense central region, a proto-sun, a protostar, in a diffuse outer region. As it contracted, the cloud began to spin faster and flatter. In its central region, as the material collected more and more densely in the middle, began to heat up. And when we hear these old myths, the Judaic and Christian example of which is the Genesis account, but they're spread over all sorts of creation myths around the world about a being or a force vitalizing, infusing light and energy, often involving a aqueous medium having to do with water and fluid and, of course, life springing out of it, but springing out of a dark, lifeless, vast void, often existing for eons, untold, timeless pasts out of which the events of the present occur. And the analogy, of course, might be taken just like all religious traditions. You can take it metaphorically, literally, and there's always layers to the metaphors and interpretations you can apply to it. Could mean the universe, could mean the solar system, it could mean human consciousness itself, coming out of the void, the darkness, behind a brain who can't quite comprehend the theory of mind of another being outside of itself. When human consciousness came on the scene, it doesn't appear like it was the first, but it appears like it was a quantum leap, a significant evolutionary leap beyond Homo heidelbergensis and definitely beyond Homo erectus and far beyond chimpanzees and bonobos. So there is the consciousness element in interpretation, but nonetheless the profundity of religious myths are often that they can be coherently interpreted in multiple ways. That can give a story, that can be one characterization of a deep story, one that can hold truths, contain and transmit truths at multiple levels of analysis. In the beginning, when God created the heavens and the earth was a formless void. Nebulae, gaseous, sparse, wispy clouds are very much formless. They are and embody the darkness of space, and even when they are lit, they are only giving off light either through reflection or from the impulse and distribution of energy from another source outside itself, or for already developing stellar nurseries from within itself. But nonetheless, ours was a formless void, most likely light years, a cloud of just light years of darkness, covering the face of the deep. mean, there's multiple depths to space. Whether it's the intergalactic voids, or just the interstellar voids, or just the voids of immaterial fluidity within nebulae themselves. All of those are deep objects. And then the instigation, the first impulse to collapse and begin a slow rotation around the center of mass, out of which would eventually materialize our star, the sun. It's often thought that protoplanetary systems are injected by the energy pluming out of supernovae within a nearby proximity, injecting a movement and momentum and energy into the particles and molecules themselves, which infuses a intrinsic instability into the system, an otherwise relatively stable, lifeless system, slowly churning cold gas. It is now injected with heat and light. The particles are moving, perhaps broken up into sections, one of which ultimately is just ever so slightly denser than the rest, and around which movement can slowly begin. And that last part of the first sentence of Genesis, and again the Egyptians and Mesopotamians and other traditions echo this same sentiment, and it's very likely, especially given all the mix and influence, cross-contamination, so to speak, of cultures around that central region, the Levant, the modern-day Turkey, Asia Minor, the whole Fertile Crescent through Mesopotamia, and east in India, and even in China. The idea that there was a wind from God that swept over the face of the waters is almost ubiquitous. And today, there's remnants of that in calling the pneuma, the wind, the spirit, when we refer to not only the wind of the earth, but the wind from the sun, the solar winds. Just keeping myself on course here. I wanted to make sure I wasn't too far off from the facts that that science indicates probably took place. The Nebular Hypothesis says that the solar system formed from the gravitational collapse of a fragment of a giant molecular cloud, probably something on the order of 65 light years across. Out of this massive cloud, a fragment, maybe 3 or 4 light years across, which would make sense given the distance to the nearest stars, were broken off and collapsed and congealed around their own centers of gravity. One of these collapsing fragments then became our solar system. The oldest inclusions found in meteorites are submillimeter to centimeter sized light-colored calcium and aluminum-rich segments Technically, an inclusion is material trapped inside a mineral during its formation. So, the oldest inclusions found in meteorites thought to trace the first solid material to form in the pre-solar nebulae are 4.5 billion years old, 4,568.2 million years old, which is one definition of the solar system. Studies of ancient meteorites found on Earth here, reveal that traces of stable daughter nuclei of short-lived isotopes such as iron-60 that only form in exploding short-lived stars. This indicates that one or more supernovae occurred nearby. And so the shock wave from a supernova may have triggered the formation of the sun by creating relatively dense regions within the cloud, which triggered a successive collapse. And so maybe the massive molecular cloud that would become the cloud from which and off of which our solar system, our proto-planetary disk, eventually broke off, was dark and cold and energy-less. But certainly within the tens of millions of years surrounding and before the onset of the first shock waves, triggering the collapse of the regions into more clearly orbiting and moving disks that would become stars, scientists think that the nebula was similar, possibly, to the Orion Nebula today, being a large star-forming region that produced massive stars. The Kuiper Belt, the massive, the very distant, almost sphere, but certainly ring of Kuiper Belt objects, being icy, rocky bodies, far, far out, 50 times the distance from our sun. So maybe something like billions, 5 billion miles away from the sun. This Kuiper Belt, the studies of the structure of it suggest that the sun formed within a cluster of stars of between 1,000 and maybe even 10,000 stars, with a diameter between 6.5 and 20 light years. It may be a collective mass of 3,000 suns. And we are drifting in this 250 million year revolution around the galaxy's center. And so maybe after about one or two of these revolutions, these 250 million year orbits, the cluster itself began to break apart. They've even done simulations of our young sun interacting with close passing stars over the first 100 million years of its life. Interesting. Scientists say that these gravitational influences would have perturbed, made anomalous orbits, such as detached objects of the far distant bodies out in the Kuiper Belt and, even the Oort cloud. Pluto is one of the largest objects in the Kuiper Belt, just so we have an idea where that is. So once the cloud broke off from its larger 60 to 70 light-year across molecular cloud, becoming its own unique, gravitationally bound entity that would become our system. The movement started allowing the increasingly more energetic interactions between particles of dust and rock and ice to form the nodes, or the seeds, around which the planets would eventually evolve. Over tens of millions of years, these particles grew to form planetesimals. Because of the conservation of angular momentum, the nebula spun faster and faster as it collapsed. As the material converged onto the central point that would become the star. Over about 100,000 years, the competing forces of gravity and the gas pressure, magnetic fields, and rotation caused the contracting nebulae to flatten into a spinning protoplanetary disk with about a 200 AU, or astronomical unit, the distance between Earth and the Sun today, 100 million miles, a 200 AU diameter. So the protostar at this point is a star in which hydrogen fusion has not begun, but it's so massive that there is conductive, convective, radiative heating, so there's going to be black body radiation simply from the heat of the friction and kinetic collisions going on within it. So it will be dimly glowing at this point. And speaking of glowing, just remembered I have my candle over here. Not to forget our mythological analysis. The second sentence of the Bible, and again many other creation mythologies, include something very similar. God said, "Let there be light." It's now within 50 million years of the initial onset of the rotation of this protoplanetary disk that the temperature and pressure at the core of what would become the Sun became so great that its hydrogen began to fuse, creating an internal source of energy that countered the gravitational contraction until a hydrostatic equilibrium was achieved. This marked the Sun's entry into the prime phase of its life, known as the main sequence. Main sequence stars are defined as deriving the most of their energy from the fusion of hydrogen into helium, one proton into a nucleus with two. The Sun today is still a main sequence star. As the now nuclear illuminated solar system, the early, young, very infantile solar system, continued to evolve. It eventually drifted away from its siblings in the stellar nursery and continued orbiting the Milky Way center on its own. And it's thought that the sun likely formed as many as 10,000 light years closer to the galaxy core. We're about 30,000 light years away from the galactic core now, so we would have been in a much more dense, much more vibrant region of the galaxy back then. So maybe it wouldn't have been as dark as I'm trying to force onto that interpretation, but nonetheless, I still find it fascinating that people 20, even 10,000 years ago could have come up with a creation mythology that is so similar to not only the physical, but the biological processes that created both life, consciousness, the planets, the solar system, and maybe even the universe itself. Now, a lot like the rings around Saturn, and even Jupiter and the other planets out there, instabilities in the rotating disk at this point caused regions within it to condense into rings under the influence of gravity. And in these rings of more dense materials at specific orbital distances, roughly circular but slightly ecliptic, of course, these regions had these planetesimals of rock and ice and dust, the seeds of these first little planetesimals, these first asteroids and cometary materials, the ones that grew the most rapidly, continued to grow more rapidly because the larger they got, the more mass they had, the more gravitational attraction they had and continued to have. And as these grew and collided into each other and other planetesimals, other massive bodies, gradually, over millions, tens of millions of years, each orbital distance from the sun was cleared out until there was nothing but planets and their moons left over. The inner solar system in particular, the region inside about 4 AU, 4 times the distance from us to the sun, was too warm and far too volatile for molecules like water and methane to condense. So the planetesimals that formed there, Mercury, Venus, Earth, Mars, could only form from compounds with high melting points, such as metals that sunk to their cores, the iron, nickel, and aluminum, and rocky silicates. Only these rocky particles and metals could remain in solid form this close to the star. Other materials like gaseous methane and hydrogen, helium, water, they were vaporized. In due course, these rocky and metallic particles gradually came together, forming, in conjunction with the other dustier, icier particles, the rocky inner planets. The cooler outer regions of the disk In this region, a similar process occurred, but the solid particles that came together there to form planetesimals contained large amounts of various ices such as water and ammonia and methane, as well as the rock. The energies in the solar winds weren't as high to blast and blow the much more sparse and loose, much less dense atmospheres of gas forming around what now today are called the gas giants. These materials were destined to eventually become the cores and the full planets, Jupiter, Saturn, and the icier Uranus and Neptune, forming farther out beyond the frost line. This frost line is the point between the orbits of Mars and Jupiter, where the asteroid belt is. This marks the point where material is cool enough for volatile icy compounds to remain solid. The ices that formed the Jovian gas giant planets, they were more abundant than the metals and silicates that formed our terrestrial planets, ours in particular, allowing the gas giants to grow massive. And they grew again, they gained their own tendency to increasingly grow and sweep away all the other particles absorbed by absorption or gravitational perturbation, in which they fling them gravitationally away after millions of orbits. And they gained all the material, all the mass, all the rocky bodies, all the nebulous, leftover interplanetary gas left over from the proto-solar nebula. The sun itself ends up being approximately 2 times 10 to the 30th kilograms. That's 2 followed by 30 zeros. Jupiter, being the next largest system in the body in the solar system, is about 2 times 10 to the 27th, about 1,000 times lighter than the sun. The sun takes up 99.86, almost 99.9% of the total mass of the entire solar system. The combined mass of all the planets, then, is only about 0.14%. That's 0.14%. 14% of a percent. 14/100ths of a percent of the entire solar system's mass is in the planets. And of that 14% of a percent of the leftover mass after the sun accumulated all of its mass, being primarily hydrogen, a smaller but still significant chunk being helium, and trace amounts of other smaller light elements like nitrogen and carbon and oxygen. Jupiter takes up about 71% of all the planetary mass. Saturn is about 21%, so that makes up 92% of the combined planetary mass between just Jupiter and Saturn alone. Neptune and Uranus then take 5 and 4%, respectively. Then Earth taking 0.3 and Venus taking 0.2% of the total planetary mass. Mars is 0.06, and Mercury, although it's a lot smaller, has a lot less volume, it's a lot more dense than the other planets. So it's just slightly less mass than Mercury. Mercury being 0.06%, Mercury is 0.05 or 0.05 of the total planetary mass. Theorists actually believe that it's no accident that Jupiter lies just beyond the frost line, being the largest planet. The frost line accumulated large amounts of water via evaporation from infalling icy material, so it created a region of low pressure that increased the speed of the orbiting dust particles and halted their motion towards the sun. So in effect, the frost line acted as a barrier that caused the material to accumulate rapidly at 5 AU from the sun. And this excess material coalesced into a large embryo or core on the order of about 10 Earth masses, which then began to accumulate rapidly in envelope via accretion of gas from the surrounding disk at an ever-increasing rate. Then, as the accumulation of further mass kept increasing, once that mass, that would become Jupiter, reached about 150 Earth masses, the solid core proceeded to increasingly grow at a very rapid pace, finally topping out at around 318 Earth masses. Saturn may owe its substantially lower mass simply to having formed a few million years after Jupiter, where there was less gas available for it to coalesce and gravitationally absorb. The Sun at this early stage was known as a T Tauri star. They're a class of variable stars that are less than about 10 million years old, and this class is named after a young star in the Taurus region. They're found near molecular clouds and identified by their optical variability and their strong chromospheric lines. The chromosphere is the second layer of a star's atmosphere, located above the photosphere and below the solar transition region and the corona. So they're a pre-main sequence star. They're in the process of contracting to the main sequence. And typically most stars of less than 3 solar masses, or 3 times the Sun's mass, which the Sun obviously fits within, follow this trajectory, this phase of stellar evolution. And these T Tauri stars, like the young Sun, have far stronger stellar winds than more stable older stars. Uranus and Neptune are thought to have formed after Jupiter and Saturn did, when the strong solar wind had blown away much of the disk material at this point. As a result, those planets accumulated little hydrogen and helium, not more than about 1 Earth mass each. So Uranus and Neptune are sometimes referred to as failed cores. The main problem with formation theories, though, for these planets is the time scale of formation. At the current locations, it would have taken millions of years for their cores to accrete. This means that Uranus and Neptune may have actually formed close to the Sun, even near or between Jupiter and Saturn, and later either were somehow migrated, or were ejected outward. It was after about 10 million years that the Sun's solar wind would have cleared away all the gas and dust in the protoplanetary disk, blowing it into interstellar space and thus ending the growth of its planets. As the radiation from the Sun blew away most of the remaining gas and other unaccreted materials in the planetary solar system, some of the leftover planetesimals in the outer part of the disk formed the vast and remote Oort cloud of comets. These are just frozen, rocky-cored, ice-veneered bodies far out into nearly interplanetary or interstellar space. The region at the very boundary of the solar winds and the solar influence. This is the field from which all comets that we've ever seen appear to originate from and orbit back into after they come close to the Sun and blow off their plumes of off-gassing ice and other gases created from the burning and vaporization of the frozen outer layer of it, and creating the famous tails that comets have when they get close enough to the Sun. It's thought that within the first 100 million years, there were as many as 100 Moon to Mars-sized protoplanets vying for gravitational dominance in the inner solar system. Further growth at this point was possible only because these bodies interacted and collided, merged, which took this full 100 million years. They would have gradually interacted and tugged at each other's orbits until they collided, merged, liquidated upon impact, with their bodies ripping open, the densest material in them falling into a single core at the center of the new planet that would become either Mercury, Venus, Earth, or Mars. At the outer edge of this inner planetary region, the terrestrial region, between 2 to 4 AU from the Sun, 2 to 4 times the Earth's distance, we have the asteroid belt. The asteroid belt initially contained more than enough matter to form 2 to even 3 Earth-like planets. And indeed, a large number of planetesimals did form there, Ceres being the largest. About 60% of the total mass of the asteroid belt is contained actually in the 4 largest asteroids, Ceres, Vesta, Pallas, and Hygeia. Total mass of the asteroid belt itself is estimated to only be 3% of the moon, of our moon. The asteroid belt is the smallest and of course innermost known circumstellar disk in the solar system. In this same category of circumstellar disk materials are groupings of objects that are less than planetary sized. The classes of small solar system bodies are the near-Earth objects, NEOs, the centaurs, which are a group of small solar system bodies in the orbit between Jupiter and Neptune. So from Jupiter, at the beginning of Jupiter, all the way out to the beginning of the Kuiper Belt. Then you have the Kuiper Belt. Then you have scattered disk objects. This is a distant circumstellar disk in the solar system that's sparsely populated by icy small bodies, which are the subset of the broader family of trans-Neptunian objects. These have highly eccentric orbits, highly elliptical, very non-circular orbits. And a trans-Neptunian object is any minor planet in the solar system that orbits the Sun at a greater average distance than Neptune, which is defined by having a semi-major axis of about 30.1 AU, or astronomical units. Now you have some very interesting phenomena regarding the orbital, the speeds, and the revolutions around the Sun, or the years of the planets, and the relations sometimes between the planets and their moons. They've, including the speeds and the distances away from the Sun, or the moons away from their planets, and the relative speeds of the orbits between planets. This resonance or ratios that you find, these interesting characteristics, are embodied in the Neptune and Pluto 3:2 resonance, where Pluto orbits the Sun twice for every 3 orbits of Neptune, in a very precise 3:2 ratio. This resonance actually helps stabilize Pluto's orbit despite it crossing Neptune's path. Jupiter's Galilean moons, the main moons observable through a simple basic telescope, Io, Europa, and Ganymede, have a 4:1 resonance with each other. These are in what's called a Laplace resonance. For every 4 orbits of Io, Europa orbits twice and Ganymede orbits once. This resonance contributes to tidal heating, particularly affecting Io and Europa. These have been locked into an exact orbit. The rotation, the velocity around the orbital speed around Jupiter. Saturn's moons have something similar going on. Mimas and Tethys have a 2:1 resonance, Enceladus and Dione 2:1, and Titan and Hyperion have a 3:4 resonance. Mercury has its own, that we've talked about before, 3:2 spin-orbit resonance. So it rotates 3 times, or has 3 days for every 2 orbits around the Sun. So it takes 2 years to have 3 days on Mercury. meaning that one day is just under the length of a year. So that's a sidereal day where it technically rotates 360 degrees 3 different times. But because it is going around the sun, and typically a rotation around its own axis of a planet is much quicker than its orbit or revolution around the sun, because it's so drastically different in the spin versus the orbital length a year, the revolution is so similar that actually creates the effect of the sun taking 2 full years, or 2 full years to go around Mercury if you were on the surface. From sunrise to sunrise would take 2 Mercurian years. The planetary distances themselves are kind of interesting in that if we say Earth is 1 AU, or 1 astronomical unit from the Sun, Mercury is almost 1/3 of that. Then Venus, the other planet in between us and the Sun, is almost just over 2/3 of that. Mars, being the only other inner planet, terrestrial planet, further from us than from the Sun, is almost exactly 1.5 times the distance from Earth to the Sun, away from the Sun. Jupiter is 5.20 exactly AU from the Sun. Saturn is almost 9.5 times the Earth's distance from the Sun. Uranus is 19.2, and Neptune is exactly 30.05 AU from the Sun. Another group of objects, subplanetesimal sized objects in the solar system that are very significant, are the million-kilometer sized objects orbiting in the exact same orbital field at the exact same distance from the Sun as Jupiter. These are called Jupiter's Trojans. It has its own set of two different asteroids that share its orbit around the Sun. And this is only possible from a period of a node of gravitational stability that forms between 2 massive bodies approximately 60 degrees above or ahead and 60 degrees behind the secondary orbiting body's position. So at any given time, in the L4 position, or Lagrange point 4, and the L5 position, you have these 2 massive groups of asteroids that bookend or surround, follow Jupiter around in its orbit around the Sun. The total number of Jupiter asteroids, Trojans, larger than 1 kilometer in diameter is believed to be 1 million, and this is approximately equal to the number of asteroids in the larger asteroid belt that are approximately the same size. So they might not have as many small asteroids, but incredibly they have as many large 1 kilometer and above asteroids in this gravitational configuration around Jupiter's orbit. It's thought that one of the 2 main theories is that it's from resonance. From about 5 to 600 million years after the solar system formed, in what's called the NICE model, the orbits of the giant planets Saturn and Jupiter became unstable. And in this theory, at the same time, encounters between the planets Uranus and Neptune caused a scattering of primordial Kuiper belt objects beyond them to throw millions of them inward towards Jupiter and Saturn, where although there might have been pre-existing Jupiter Trojans at that point, Jupiter eventually captured millions of new objects in this event. Another theory about the emergence and formation of the Jupiter Trojans suggests that they formed in the same part of the solar system as Jupiter and entered their orbits while it was still forming, but during the last stage of Jupiter's formation, its formation involved a major runaway growth in its mass through the accretion of just large amounts of hydrogen and helium from the still remaining protoplanetary disk. And during this growth, which lasted for only about 10,000 years, which is a blink of an eye on cosmic scales, the mass of Jupiter increased by a factor of 10. The planetesimals then had approximately the same orbit as Jupiter. They were a little more loosely concentrated. At this point, over this small period of time, the increased gravity of the planet consolidated them and captured them and corralled them neatly into the Lagrangian orbits that they occupy today. Scientists proposing this model think that the capture mechanism was extremely efficient. About 50% of all remaining planetesimals in this region between Mars and Saturn would have been trapped. The inner solar system's period of giant impacts probably played a role in Earth acquiring all its water content, the massive, almost identifying volume of water that our blue planet has today. Water is much too volatile to have been present at Earth's formation, so scientists think that it must have subsequently been delivered from outer, colder parts of the solar system, of course, during which it would have evaporated and melted upon impact, while some might have escaped. Once the Earth's mass was large enough to have a gravitational field significant enough to retain an atmosphere, the impacted gas and water vapor would have been significantly bound to the Earth at that point. The water was probably delivered by planetary embryos and small planetesimals thrown out of the asteroid belt by Jupiter. A population of main belt comets discovered in 2006 has also been suggested as a possible source for the Earth's water. Now, in contrast, comets from the Kuiper belt or further out in the Oort cloud delivered probably not more than 6% of Earth's water. And it's this period of the accumulation of material and debris where the panspermia hypothesis may come into play, in that if life was created elsewhere in the universe prior to our solar system's formation, the sun and the protoplanetary disk at some point could have contained external, extrasolar life, upon which the asteroid impacting Earth, containing it, would have germinated, would have planted the seeds of life on Earth for it to evolve hundreds of millions of years later, over slow emergence of conditions that would have allowed the bacteria or protobacteria to eventually thrive, as bacteria can be dormant for very long periods of time, and in certain types of bacteria that would have been able to survive in space can withstand extremely harsh environments. There's lots more, of course, to talk about with the history of something as grand and important to us as the solar system, but that's all I have time for today, guys. Thanks so much for subscribing. Thanks for liking the videos. Thanks for leaving comments, showing love, and or giving constructively criticizing thoughts, about the videos. So I appreciate you watching, and we'll see you in the next one.